Okay, in our last lecture, we talked about correlations for internal flow. Right? We talked about specifically how you can access them. We focused on using them in ease, but obviously correlations can be found in any book, any heat transfer book, in any handbook of heat transfer. You're going to find just a catalog of these different correlations. For an internal flow, the correlations that we care about are going to be the friction factor, and we're using the Moody or the Darcy friction factor, and the Nusselt number. And again, depending on what kind of information we're after, we might either want the local friction factor or the average friction factor. So this would be pressure gradient, this would be total pressure change, and the same thing here, the local heat transfer coefficient you get with the local Nusselt number, or the average heat transfer coefficient with the average Nusselt number. So we have kind of those in our pocket now. We know where to go get them. But one last thing we have to understand before we can actually solve internal flow problems is how we do an energy balance on an internal flow. So an internal flow is a little bit more complicated than an external flow. So for an external flow, so flow over a plate or a cylinder or something like that, if you think about it, it was simple in the sense that as you moved away from the surface of the body that you were studying, if you move far enough and you get through the boundary layer, you always get to a free stream temperature that doesn't change. T infinity is constant no matter where you are on the surface. For an internal flow, you have this mean temperature, and this mean temperature changes as you move along in the flow direction, right? As you add or remove energy from the flow, what that does is it changes the energy carried by the flow, it changes the mean temperature. The heat transfer coefficients that we get with those correlations are based on the mean temperature. So in order to actually solve these problems, I have to know how is the mean temperature changing as you move through the duct. And the way that you get that information is you do an energy balance. So for an internal flow, for an external flow, all you had to do to solve the problem was use a correlation, right? For an internal flow, you actually have to use a correlation and also solve an energy balance, right? When we get to heat exchangers, which have multiple fluids moving through ducts, you'll have to use two correlations and solve two energy balances, right? So it's going to get one layer even more complicated than this. But for today, let's focus on a single fluid flowing through a duct and think about how we're going to do an energy balance. So here's the energy balance that we're going to use. This is differential in terms of x, so it's differential in the flow direction, but it extends all the way across the cross section of the duct in the other dimensions, right? So it's the same control volume that we used when we were trying to figure out the pressure gradient and how it was related to the shear stress and the momentum of the fluid. The reason we can use this control volume rather than one that's actually differentially small in x and y is because we're thinking about the mean temperature, which characterizes the total flow through this control surface, and also we have hopefully somewhere in our pocket the heat transfer coefficient, which characterizes the interaction between the wall and the fluid, right? And that's actually kind of subtle but kind of important, right? If we don't have access to a correlation that'll give us the heat transfer coefficient, then this control volume is completely useless to us, right? So the reason I can use this control volume, which gives me an ODE for temperature, for mean temperature, is because somebody else has already solved the very detailed problem associated with the two-dimensional temperature distribution of the flow, and they boiled that solution down to a heat transfer coefficient that I can use, right? All right, so this is the control volume that we're going to use. It is differentially small in the flow direction. I have to think about all the different energy terms that might be in this control volume. So we have in equals out plus stored. So let's start with stored. There would be a stored term here if this were a transient problem. So if the temperature of the fluid were changing with time. The fact that I didn't include that in this control volume means that we're only going to use this for steady state. So what I've drawn here is a steady state control volume. What else? We know that there can be viscous dissipation whenever fluid is flowing, right? That viscous dissipation would lead to a generation of thermal energy, and I did not include that in this control volume. So that says I'm ignoring that phenomena. And the reason I'm going to ignore that is because somewhere I've calculated the Eckert number over the Reynolds number and found that it's small enough relative to 1 that I don't have to think about viscous dissipation. There can be axial conduction, right? So I could have conduction of heat through this surface and through this surface. That's certainly going on if there's a temperature gradient in the fluid. I didn't include those terms here, and so that says that I'm ignoring axial conduction, right? And the reason that I can ignore axial conduction is because, as we talked about before, the Peclet number, the product of the Reynolds number and the Prandtl number, must be sufficiently higher than 1 that term is small. So what terms did I include? So I have included the energy carried by the flow, which is typically a dominant energy term. So that's coming in through this surface at location x and is leaving through this surface at location x plus dx. And that energy carried by the flow is m dot times the specific enthalpy of the flow, which in this class we used the symbol I to indicate, not h, but I, because h is obviously used for heat transfer coefficient everywhere. It's super confusing if you use h for heat transfer coefficient and also for enthalpy, so we're going to use I for enthalpy. So yeah, this is the change in the energy carried by the flow. Why does the energy carried by the flow change? Well, because you are either adding or removing energy out here at the surface of the duct, right? So this is the convective heat transfer between the surface and the flow. This I can characterize with a heat transfer coefficient, and the area over which it acts is the perimeter exposed to fluid. So this is the heated perimeter times dx. So if we throw those terms together into an energy balance, we have in equals out. There's no stored. I'll do the usual thing where I expand this x plus dx term. So this is x, and then dm dot times I dx times dx. We can cancel these two terms out. And then the other thing I'm going to do is recognize that continuity tells me that the mass flow rate doesn't change as I move through here, so I can pull that out of the derivative. We cancel the dx's out, and here's my differential equation. The last thing I'm going to do is assume this is an incompressible substance, so that di is equal to c dt. That also assumes that whatever enthalpy change is driven by a pressure change, I'm going to ignore in favor of the enthalpy change driven by a temperature change. Right? So that gets me to this differential equation, which is the one that we almost always use. Right? This is saying that the rate of heat transfer that I inject at the surface is going to changing the temperature of the fluid as it travels through the duct. This should make a lot of sense, right? If I am adding energy at the surface, if I have a positive heat flux here, I would expect the temperature of the fluid to increase with x. The other thing I can do, depending on what's given to me and what's not, is I can recognize that this rate of heat transfer is the convective rate of heat transfer, so it is h times ts minus tm, right? And again, the fact that I have this h, right, the only way this is a useful energy balance is if I can somehow get this h, says that somebody else has solved the details of the flow for me so that I can represent those details in this single parameter called h. So this is the energy balance. This is the ODE. They're equivalent, right? These are the ODEs that I have to solve in order to understand how the mean temperature is varying with position in the duct. So there's at least two different cases. I guess going back here, in order to decide which of these forms I'm most interested in, I have to know what's going on at the surface of the duct. So that information can be given to you in a few different ways. One way, the easiest way to deal with, is if somebody tells you what the heat flux is as a function of position, right? So that's a specified heat flux condition. Somebody says, maybe I've wrapped this tube with heat tape. The heat tape gives a constant heat flux. So now you know exactly what the heat flux is at the surface of the duct. If that were the case, then this upper ODE is perfect, right? Because you know the heat flux, it's prescribed for you, and you can just solve this. The other situation might be somebody tells you what the temperature at the surface of the duct is, right? Maybe you've immersed this tube in a big pot of boiling water, so you know the temperature of the surface of the duct is the temperature at which water boils. So that's a case where then this bottom ODE is more useful because now you know the surface temperature, right? So you know one of those two things, or at least a relationship between them, and that's going to give you the information you need to actually solve this ODE, right? So let's look at the first case. The first case is I know the heat flux. So I have a specified heat flux. It might be a function of x, but I know what that function is. So this then is a very easy ODE to solve, right? I would separate it. So I'm going to bring the dx over here along with the m dot c. So that's what I've done here. And then I leave the dt over here. I'm going to integrate. So I'll integrate from x equals 0 to x, and that takes me from the temperature at x equals 0, which is the inlet temperature of the fluid, to T sub m. And if I solve this, I get this equation, right? And this equation basically tells me how is the mean temperature changing as a function of position. And you can see here the mean temperature is just responding to how much heat I've put in, right? The rate at which the mean temperature is changing is exactly proportional to the rate at which I am putting in heat, right? And this is just doing that integration. If I want the surface temperature, so this equation tells me nothing about the surface temperature, right? If I want the surface temperature, then I have to bring in the heat transfer coefficient. So the difference between the surface temperature and the mean temperature, the temperature difference required to drive the heat into the fluid, that's related to the heat transfer coefficient, right? It's the heat flux divided by the heat transfer coefficient. So, if we have a special case, here's the simplest of the prescribed heat flux cases. It's one where I have just a constant heat flux on the duct. What would that look like? Well, if I go back up here, you can see that if the heat flux is constant, then that tells me that the rate of change of the mean temperature is constant, right? The gradient of the mean temperature is constant. So I come in at Tn, and this black line says I just increase linearly, and that should make perfect sense, right? It doesn't matter what the heat transfer coefficient is. And energy balance just says that the energy carried by the flow is just going to increase linearly because I'm adding heat at a constant rate, right? If I add more heat, if this goes up, I'm going to increase faster. If I add less heat, this slope is going to go down. If I want to know what the surface temperature is, well, then I have to come and look at this equation here. So this says that the surface temperature is going to be elevated relative to the mean temperature based on what is the rate I'm adding energy, and then divide that by the heat transfer coefficient. So if I have a really high heat transfer coefficient, I would expect the surface temperature to the mean temperature difference to be small. That makes sense, right? I have a high heat transfer coefficient that says, the fluid is really intimately coupled to the wall. If I have a low heat transfer coefficient, then it's going to take a larger temperature difference. So, here at the very inlet to the duct where the boundary layer is really small, the heat transfer coefficient is really high, I would expect that the surface temperature and the mean temperature are pretty close to one another. And then as the boundary layer grows, the heat transfer coefficient gets smaller and smaller, I would expect that temperature difference to get larger and larger, right? That temperature difference is the heat flux over the heat transfer coefficient. Eventually, I get to a thermally fully developed region in my duct, right? I get to that thermal entry length. At that point, the heat transfer coefficient doesn't change anymore. And for this particular problem, the heat flux doesn't change anymore either. So I would expect a uniform or a constant difference between the mean temperature and the surface temperature, right? And you can do all kinds of things with the heat flux, and that will change how the mean temperature changes, and you just have to sort of look at what your problem is telling you in order to draw a graph that looks like this. All right, the other situation you can get is one where you have a specified surface temperature, right? So if you have a specified surface temperature, this form of your ODE is not that useful anymore because the heat flux is not constant and it's not known, right? What I know is the surface temperature. So I'm just going to substitute this equation into this equation to get this equation. And now I have an equation that's actually at least solvable, right? I have the rate of change of my mean temperature is given to me in terms of whatever the surface temperature happens to be and the mean temperature. And if you look at this for a second, you realize this is a state equation, right? I can solve this equation using whatever numerical technique I'm most comfortable with, because I can just step it through not time anymore, but position, and move my way down the duct, right? Whatever Runge-Kutta fourth order technique I want to use, or whatever it is, I can move through the duct. If you have the special case of having a constant surface temperature, that is the one time where it's possible to analytically solve this, right? So that's one where you bring the temperature stuff over here, you bring the dx over here, and you integrate both sides, recognizing that heat transfer coefficient is a function of position, right? So I cannot pull this out unless I'm entirely in the fully developed region. I cannot pull this heat transfer coefficient out. So I integrate both sides. If you do the math, what you'll realize then is that the mean temperature behaves according to this equation here. So it approximately exponentially approaches the surface temperature. And I say approximately exponential because this heat transfer coefficient, this average heat transfer coefficient, actually depends on where you're at. So it's not truly an exponential. So that's the two cases that we're going to look at least today. And I guess the next thing to do is actually do an example problem. So we're going to do an example problem where we have to bring both of these two pieces together. And by that I mean we have to go use the correlations so that we understand, the heat transfer coefficient and the friction factor and that kind of stuff. And then separately, we also have to do an energy balance so we understand how the mean temperature is changing, right? And once we do that, it should be enough for you to do your homework problem.